You are aboard a ship that has already passed the point where turning back is possible. Behind you, Earth is not a planet anymore. It is a memory of brightness, fading. Ahead of you, 1,100 trillion kilometers away, waits the nearest known black hole. A wound in space so complete that not even light, the fastest thing in the universe, has ever found a way back out of it. Most people picture a black hole as a hole, a pit, an absence. But here is the part almost no one says clearly. There is no hole. There is only gravity, bent so far past its limit that space itself folds in on a single point and never unfolds again. What you are approaching is not an object. It is a verdict, written permanently into the shape of the universe. And the closer your ship drifts toward it, the less anything you know about distance, time, or your own body will continue to apply. If you enjoy deep space and science content, do me a small favor, hit that like button and subscribe. It genuinely helps this channel grow, and there is much more like this coming. Make yourself comfortable. Let's begin. Before there was an image of a black hole, there was only an idea. And the idea arrived 130 years before anyone had the instruments to test it. In 1783, an English clergyman named John Michell sat with the mathematics of gravity and asked a question that, at the time, sounded almost absurd. If light behaves like a stream of particles, he reasoned, and if gravity pulls on everything with mass, then perhaps a star could grow massive enough and dense enough that even light could not escape its surface. He called these hypothetical objects dark stars. He had no way to observe one. He simply trusted the arithmetic, and the arithmetic told him that somewhere in the universe there might be places that swallow their own light and give nothing back. For more than a century, the idea waited. It waited through the death of Newtonian physics as the final word on gravity, and it waited through the early, uncertain years of a new theory that would replace it. In November of 1915, Albert Einstein published his General Theory of Relativity, a description of gravity not as a force reaching across empty space, but as the curvature of space and time themselves, bent by the presence of mass. It was a beautiful theory. It was also, by Einstein's own admission, nearly impossible to solve in its full form. The equations were too complex, too tangled, for anyone to extract a clean, exact answer. It took less than 2 months. In December of 1915, a German astronomer named Carl Schwarzschild, serving on the Russian front during the First World War, found something almost no one expected. Working through Einstein's equations by hand, likely between military duties, in a place built for nothing but survival, Schwarzschild produced an exact solution. It described the space-time around a perfectly spherical, non-rotating mass. Buried inside that solution was a number, a radius, at which the mathematics broke down entirely. At that radius, escape velocity equaled the speed of light. Beyond that point, by the theory's own logic, nothing could escape. Not a signal, not a photon, not information of any kind. Schwarzschild sent his result to Einstein from the trenches. He died several months later, in May of 1916, from an illness contracted during his military service. He never lived to see what his solution would eventually be understood to mean. And for decades, almost no one believed it meant anything physical at all. Einstein himself doubted that such an object could actually form in nature. He suspected the mathematics described a kind of theoretical limit, never realized by an actual star. Many physicists agreed with him. The Schwarzschild radius was treated as a curiosity, a strange artifact buried inside an equation, rather than a real boundary that real matter could cross. It took most of the 20th century to change that consensus. Theoretical work in the 1930s, then renewed mathematical attention in the 1950s and 1960s, slowly built the case that collapsed stars really could cross this threshold, and that the universe was not merely capable of producing such objects in principle, but was very likely producing them constantly in the deaths of massive stars across every galaxy. In 1967, the physicist John Wheeler, speaking at a conference, used a name that stuck where decades of more technical language had failed. He called them black holes. The name was simple enough to survive in public memory and accurate enough to survive in physics. Still, for most of the 20th century, a black hole remained something inferred, never something seen. Their presence was detected only through its effects: stars orbiting something invisible, X-rays pouring from matter being torn apart at the edge of something with no visible surface, gravitational waves rippling outward in 2015 from two black holes spiraling into one another and merging into a single, larger one. Evidence accumulated for a century without a direct image. That changed in April of 2019, when the Event Horizon Telescope collaboration released the first image ever captured of a black hole's shadow, the supermassive object at the center of the galaxy M87, 55 million light-years away. In 2022, the same collaboration produced an image of Sagittarius A star, the black hole at the center of our own galaxy. Both images showed the same basic shape: a dark center, ringed by the glowing, distorted light of matter, being pulled toward an edge it could never recross. We have, in a very real sense, seen the shadow of a black hole. We have never seen, and by the nature of the object itself, may never see, what lies beyond that shadow's edge. The boundary keeps its secrets by design. It is the only object in the known universe built by the laws of physics themselves to be unknowable from the outside. So the question becomes unavoidable. If we cannot see beyond that edge from here, what would happen if something crossed it? Not in theory, not in simulation. What would actually happen, step by step, to a ship and the people inside it if they began the journey toward the nearest one we know of and did not stop? So begin with the simplest part of the question and let it turn out to be the hardest. Where would such a ship even go? For most of human history, the answer would have been nowhere, because no one knew of a single confirmed black hole close enough to name. That changed in 2022, when astronomers using data from the European Space Agency's Gaia spacecraft identified something unusual in the motion of an ordinary Sun-like star roughly 1,600 light-years away, in the constellation Ophiuchus. The star was wobbling, not randomly but rhythmically, in a pattern that could only be explained by an unseen companion pulling on it with enormous, precisely measurable gravity, while emitting no detectable light of its own. The unseen companion, astronomers concluded, was a black hole roughly 9.8 times the mass of our Sun, orbited by its visible companion star at a distance similar to the gap between our own Sun and Earth. It was named Gaia BH1. At the time of its confirmation, it was the closest known black hole to our solar system. This is your destination. So let us be honest, immediately, about the distance involved. 1,600 light-years sounds almost conversational, said aloud. It is not. A single light-year is the distance light travels in 1 year, moving at its fixed, unbeatable speed of 299,792 kilometers per second. Multiply that speed across a full year, and you get roughly 9.5 trillion kilometers in a single light year. Multiply that by 1600, and the distance to Gaia BH1 comes out to approximately 15 quadrillion kilometers. To make that number mean something, consider this. If you could somehow travel at the speed of light itself, the fastest speed permitted anywhere in the universe, the journey would still take 1600 years. Generations of a single family, born and dying aboard the ship, would pass before arrival, even at a speed physics forbids anything with mass from reaching. And we do not travel anywhere close to the speed of light. Not yet. Not with anything humanity has ever built. The fastest object humans have ever launched is NASA's Parker Solar Probe, which, during its closest passes by the Sun, reaches speeds of approximately 690,000 kilometers per hour. That sounds immense, and by every human standard, it is. At that speed, you could circle the entire Earth in just over 2 minutes. But measured against the speed of light, Parker Solar Probe is moving at roughly 0.06% of light speed. To reach Gaia BH1 at that velocity, the journey would take not 1600 years, but more than 2.5 million years. For context, 2.5 million years ago, no member of our species existed. The genus Homo itself was only beginning to emerge in East Africa. An entire arc of human evolution, from early tool-making hominids, to cities, to written language, to spacecraft, would need to repeat itself in its entirety, twice over, before such a ship, at our fastest current speed, would arrive. This is the first and, in some ways, the most quietly devastating fact about this journey. Before any event horizon, any tidal force, any relativistic hazard becomes relevant at all, the distance alone defeats the trip. Most fictional depictions of black hole exploration skip this part entirely. A ship simply arrives, off-screen, between scenes. But there is no version of current physics, or even speculative near-future physics, where that arrival happens easily, or soon, or within a human lifetime, using anything we have built or seriously designed. So let us do what the thought experiment requires, and what honest physics insists on at the same time. Let us grant, for the sake of asking the next question, that propulsion is solved. Let us imagine a ship capable of reaching some significant fraction of light speed, perhaps 10%, perhaps 50%, through methods that remain theoretical but are not violations of known physics. Even granting that generous assumption, even setting aside the unsolved engineering of how such speeds would actually be reached, a second problem appears immediately, and it is one that no propulsion breakthrough can solve. The faster you go, the more dangerous the empty space in front of you becomes. So set the fuel problem aside, the way the thought experiment requires, and grant the ship its impossible engine. Even then, speed itself becomes a kind of danger, one that has nothing to do with the black hole waiting at the end of the journey, and everything to do with the seemingly empty space in between. Interstellar space is not truly empty. It contains a thin scattering of hydrogen atoms, dust grains, and stray particles, spread so sparsely that, at ordinary speeds, a ship could cross light years of it and barely notice the difference. But speed changes the relationship between a ship and the matter in its path, in a way that has nothing to do with how much matter is actually there, and everything to do with how fast the ship is moving through it. Consider what physicists call relative kinetic energy, and consider it the way an engineer would have to. Kinetic energy does not increase in a straight line with speed. It increases with the square of speed. Doubling a ship's velocity does not double the energy of an impact with a stray particle. It quadruples it. At 10% of light speed, A single hydrogen atom striking the ship's hull carries kinetic energy roughly equivalent, scaled to its tiny mass, to a small caliber bullet striking a single microscopic point. At 50% of light speed, that same atom's impact energy increases by a factor of 25 over the 10% case, concentrated into an area smaller than the head of a pin. Multiply this single particle effect by the sheer number of atoms a fast-moving ship would encounter every second across years of travel, and the front of the ship is no longer flying through emptiness. It is flying through a continuous, low-grade bombardment. This is not speculative engineering. It is a well-documented hazard in the serious literature on interstellar travel, discussed openly by physicists working on projects like Breakthrough Starshot, a real research initiative exploring whether small, light-driven probes might someday reach nearby star systems at a meaningful fraction of light speed. Even at the comparatively modest velocities those probes are designed for, the interstellar medium is treated as a genuine engineering hazard, not a background detail. For a crewed ship, the math becomes considerably worse, because mass that protects a human body is mass that must be accelerated, and mass that must be accelerated is fuel that must be carried, and fuel that must be carried returns us directly to the exponential cost we have already discussed. Shielding thick enough to meaningfully protect a crew compartment from relativistic particle bombardment would need to be measured in meters of dense material, not the thin aluminum skins of current spacecraft. That shielding's mass would, in turn, increase the fuel required to accelerate the ship in the first place, which increases the mass of fuel storage, which increases the mass requiring shielding. Engineers call this the tyranny of the rocket equation. It is not a metaphor. It is a closed loop with no comfortable exit, where every solution to one problem makes the next problem larger. In simple terms, the ship would need to be heavily armored to survive its own velocity, and heavily armored ships are, by definition, harder to accelerate to the velocities that make the armor necessary in the first place. So suppose, for the sake of continuing the thought experiment, that some future material solves this too. Suppose the shielding exists, light enough not to defeat the propulsion, dense enough to absorb the bombardment. The ship survives the crossing, 1600 years pass, or some compressed version of that time, depending on how close to light speed the ship actually travels. And eventually, after generations, or after whatever number of subjective years the ship's clock records, something appears ahead that was, until this point, only a number on a screen and a point of light too faint to resolve directly. It is not a hole. It has never been a hole. What it actually is requires understanding what a boundary in space-time even means, and that requires returning to the mathematics Carl Schwarzschild worked out from a trench, more than a century ago, almost as an afterthought to a war that would later claim his life. So return, for a moment, to that trench, and to the number Carl Schwarzschild found buried inside Einstein's equations. The number is called the Schwarzschild radius, and despite the century of mystery that has accumulated around it, it is, at its core, a remarkably simple idea. Every object with mass has an escape velocity, the speed something would need to travel to break free of that object's gravity forever. Earth's escape velocity is about 11 kilometers per second. The Sun's is around 618 kilometers per second. The Schwarzschild radius asks a different question. For a given mass, how small would that mass need to be compressed for its escape velocity, at its surface, to equal the speed of light itself? Compress any amount of mass down to that radius, and something changes that no later force can undo. Even light, moving at the one speed nothing in the universe can outrun, would not be fast enough to leave. The formula itself is almost embarrassingly short. The radius equals roughly 2.95 kilometers for every solar mass of material compressed into the sphere. Our own Sun, with its actual radius of around 700,000 kilometers, sits nowhere near this threshold. To turn the Sun itself into a black hole, every gram of its mass would need to be compressed into a sphere with a radius of under 3 kilometers, smaller than most cities, while losing none of the mass that produces its gravity. The Sun, as it happens, will never do this. It lacks the mass required to collapse that far. Gaia BH1, the object at the end of this hypothetical journey, has roughly 9.8 times the mass of our Sun. Multiply Schwarzschild's simple ratio by that mass, and the event horizon, the boundary itself, works out to a radius of approximately 29 kilometers. To put that size in human terms, 29 kilometers is roughly the distance across a mid-sized metropolitan area, the kind of span you might cross in a long, deliberate drive through a city and its surrounding districts. Compress nearly 10 suns worth of mass into a sphere that size, and you have built, by definition, an object that nothing escapes. This is, without question, the single most counterintuitive fact in this entire subject, so it is worth letting it settle. The event horizon is not a wall, it is not a membrane, a surface, or a shell with any physical substance. There is, by every serious model we have, nothing material located at the event horizon at all. It is a mathematical boundary, a description of where escape becomes geometrically impossible, drawn through ordinary, otherwise unremarkable space. If you were the one approaching it, falling toward Gaia BH1 in your impossible, well-shielded ship, here is what current physics tells us you would experience, locally, at the moment of crossing. Nothing. No flash. No resistance. No wall to strike or membrane to pass through. From your own reference frame, inside your own falling ship, the event horizon would not announce itself at all. You would simply continue falling, and at some point you would have crossed a threshold that the rest of the universe could no longer see past, without any local signal telling you the crossing had occurred. This single fact dismantles almost everything popular fiction has trained people to expect. There is no dramatic boundary to brace against. There is no visible edge rushing up to meet the ship. The boundary's entire nature is that it offers no local warning, no felt threshold, no instrument reading that flips from safe to unsafe in a single dramatic instant. It is a verdict written into the geometry of space itself, silent and absolute, announced only by its consequences, never by its arrival. But silence at the horizon does not mean safety on the way there. Long before a ship would reach this boundary, something else, something far more immediate and far more violent, would already be acting on it. Gravity, it turns out, is never one single force pulling evenly on an object. It is millions of slightly different forces, pulling on every part of that object by a slightly different amount, and near an object as compact as Gaia BH1, that difference becomes the thing that ends the journey first. So set aside for a moment the horizon itself, and look instead at what happens slightly before it. Because for a black hole the size of Gaia BH1, the journey ends before the boundary is ever reached. Gravity, as Newton first described it, weakens with distance, and it weakens according to a precise, predictable rule. Double your distance from a mass, and its gravitational pull on you drops to 1/4 of its previous strength. This rule sounds harmless in the abstract, the kind of detail that belongs in a textbook and nowhere else. But it has a consequence that becomes violently relevant the closer an object gets to something as compact as a black hole. If your feet are closer to the black hole than your head, your feet experience measurably stronger gravity than your head does, even though the distance between your feet and your head is only about 2 meters. Near an ordinary planet, like Earth, this difference is so small it is completely undetectable to a human body. Near a stellar mass black hole, the difference becomes the dominant force acting on you. Physicists call this differential pull tidal force, the same basic mechanism, scaled up almost beyond recognition, that causes Earth's oceans to bulge slightly toward the Moon. Near a compact object like Gaia BH1, the effect intensifies enormously as distance shrinks, because the rate of change in gravity's strength becomes extreme at short range. At some point during the approach, the difference in pull between your feet and your head would exceed the structural strength of the human body itself. Your feet would be pulled forward with measurably greater force than your head, and the unfortunate informal name astrophysicists actually use for what happens next is spaghettification. It is not a term coined for the sake of public consumption. It appears, used with a straight face, in genuine astrophysics papers, because it is, very simply, the most accurate description of the outcome. Here is where the size of the black hole changes everything, and where Gaia BH1's specific mass becomes important to the story rather than incidental to it. For a supermassive black hole like Sagittarius A star or M87 star, the tidal forces at the event horizon itself are actually survivable, in the narrow technical sense that the differential pull across a human body, even at the horizon's boundary, would not yet be lethal. Spaghettification for those giants happens deep inside the horizon, well after the point of no return has already been crossed. But for a stellar mass black hole, an object in Gaia BH1's weight class, the math runs in the opposite direction. The tidal forces become lethal at a distance, still well outside the event horizon. A human body approaching Gaia BH1 would be torn apart by gravity's unevenness before ever reaching the boundary that, in popular imagination, marks the true point of no return. In simple terms, the smaller and denser the black hole, the earlier in the approach the destruction begins. Gaia BH1, at under 10 solar masses, sits firmly in the category where this matters. Calculations based on its mass and the structural limits of human tissue suggest the lethal tidal threshold would be crossed at a distance of several hundred kilometers from the center, still comfortably outside the 29-kilometer event horizon itself. To put a number on what the body would experience, consider documented research on human tolerance to acceleration and sustained gravitational force. Trained fighter pilots in centrifuge studies have tolerated sustained forces of around 9 times Earth's gravity for brief periods before losing consciousness, and forces beyond roughly 12 to 15 times Earth's gravity, sustained for more than a few seconds, are associated with serious injury or death in documented aerospace medical literature. The tidal forces near a stellar mass black hole, at the distance where spaghettification becomes lethal, exceed these survivable thresholds by factors of thousands, escalating not gradually but within a span of mere seconds as the ship continues falling. This is not the misty, ambiguous crossing that science fiction tends to depict, where a ship simply vanishes into a swirl of light. It is destruction with a calculable schedule, a countdown written into the geometry of the approach itself. finishing its work before the more famous boundary is ever reached. To put a nose, only for the sake of the next question, that the black hole at the end of this journey were not Gaia BH1, but something supermassive instead, something where a human body could, in principle, survive the crossing of the horizon itself. Even granting that generous hypothetical swap, a second force would already be acting on the ship, one that has nothing to do with tides and everything to do with the nature of time. So set aside the tides for a moment and the lethal arithmetic of a stellar mass black hole's gravity, and consider instead what would happen to the one thing every part of this journey has quietly assumed stays constant from beginning to end: time. Einstein's general relativity does not only bend space near a massive object, it bends time as well, and it does so in a way that is neither metaphorical nor speculative. It has been measured repeatedly in ordinary, everyday technology that has nothing to do with black holes at all. The satellites that make up the global positioning system orbit Earth at high altitude, far enough from the planet's mass that time, for them, runs measurably faster than it does for someone standing on the ground. The effect is tiny, a matter of microseconds per day, but it is large enough that GPS satellites carry onboard atomic clocks specifically adjusted to compensate for it. Without that correction, position errors would accumulate at a rate of several kilometers per day, rendering the entire system useless within hours. This is gravitational time dilation, real, measured, and quietly built into a system carried in most people's pockets. The effect was confirmed even earlier, and far closer to home, in 1959, in a basement at Harvard University. Two physicists, Robert Pound and Glenn Rebka, built an experiment to measure how gravity affects the frequency of light traveling a mere 22.5 meters from the top of a tower down to its base. The predicted effect was almost absurdly small, a shift of a few parts in 10 quadrillion. And yet, using extraordinarily precise techniques involving radioactive iron and careful detection of gamma rays, they measured it and found a result matching Einstein's prediction to within better than 10%. It remains one of the most elegant confirmations in the history of experimental physics, often cited in textbooks as proof that relativity is not abstract mathematics, divorced from the world, but a description of something genuinely happening, measurably, in ordinary matter. Gravity bends time, even across the height of a university building, and we have known this with direct measurement since before the moon landing. Near a black hole, this same effect does not occur in microseconds or parts in 10 quadrillion. It becomes total. As an object falls toward a black hole's event horizon, time, as measured by someone watching from a safe distance, appears to slow for that falling object. Not gradually in a smooth, easily described way, but asymptotically, meaning the falling object's clock appears to tick slower and slower, approaching, but by the outside observer's measurement, never quite reaching the moment of crossing. From the perspective of someone watching from a ship in stable orbit, or from Earth itself, if such a vast distance allowed any signal to arrive at all, the falling ship would appear to slow as it neared the horizon, its light stretching toward longer and longer wavelengths, dimming, reddening, and never visibly completing the crossing. To the outside observer, the ship seems to freeze, forever approaching a boundary it never quite touches. This is, incidentally, why some of the earliest researchers working through Einstein's equations in the 1950s briefly favored a different name for these objects altogether. Before John Wheeler's term took hold in 1967, Some physicists refer to them as frozen stars, describing exactly this effect, the way collapsing matter would appear to a distant observer, to slow and freeze at the threshold rather than visibly vanish. The name fell out of use because it described only the outside view and missed what was actually happening to the collapsing object itself from its own perspective. But it captured something true and lasting about how strange this particular asymmetry would look to anyone watching from far away, forever. From inside the falling ship, none of this applies. Locally, in the falling ship's own reference frame, time passes normally. The crossing, when it happens in finite ordinary time, the same kind of subjective experience as any other moment in the journey. There is no slowing, no freezing, no sensation of being suspended. The asymmetry exists entirely between observers, not within any single observer's own experience. The falling traveler ages normally. The watching observer sees something that never finishes. In simple terms, two completely accurate descriptions of the same single event would coexist simultaneously, depending entirely on where you happen to stand to watch it. This is one of the strangest and most well-established consequences of general relativity, confirmed not through speculation, but through decades of consistent agreement between theory and every relevant astrophysical observation we have made since. Imagine, for a moment, someone you love standing somewhere safe, watching you fall. Not for an afternoon, not for a few anxious hours, for the rest of their life, and the rest of their children's lives, and the rest of every life that follows after that, always watching a ship that appears to be still falling, never quite arriving, never quite gone. That is what the outside view of this crossing would actually look like, stretched out across more time than any single human life could hold. Generations on the world they left behind would be born, would live entire lives, and would die, still watching the same dimming, reddening light, still waiting for an arrival that, from where they stood, would never visibly complete itself. But before any of this asymmetry becomes the most pressing problem, something far less abstract and far more immediate would already be threatening the ship. Most journeys toward a black hole never get this close to the boundary in the first place, not because of tides and not because of time, but because of something that kills first, silently from a distance: radiation. So consider now why the actual approach to most black holes never resembles a slow, careful drift toward a quiet boundary at all. For the majority of black holes scattered across our galaxy, the danger arrives long before tides and long before any meaningful time dilation, because most black holes are not quiet. When a black hole has nearby matter to draw in, that matter does not fall directly inward in a straight line. It spirals, forming what astronomers call an accretion disk, a flattened, rotating structure of gas and dust drawn steadily toward the boundary by gravity. As that material spirals closer, friction between particles moving at different speeds heats it to extraordinary temperatures, often reaching millions of Kelvin, hot enough that the disk itself glows brilliantly across the electromagnetic spectrum, radiating enormous amounts of energy, including intense X-rays, long before any of that matter actually crosses the horizon. To put a single number in human terms, the inner edge of an active accretion disk can reach temperatures of around 10 million Kelvin, roughly equivalent to the temperature found deep in the core of an ordinary star, except produced not by fusion, but by the simple, violent friction of falling. Even our own galaxy's relatively quiet supermassive black hole, Sagittarius A star, occasionally demonstrates what an active feeding episode looks like. In 2014, astronomers tracked a gas cloud, designated G2, on a close approach to Sagittarius A star, watching closely to see whether the encounter would trigger a dramatic flare as the cloud was shredded and consumed. The cloud survived its closest approach largely intact, surprising researchers and suggesting it may have been denser or more compact than originally estimated, perhaps even containing a star at its core rather than being pure gas. Astronomers have also documented sudden, dramatic X-ray flares from the same vicinity at other times, including one especially notable infrared brightening event observed in 2019, when Sagittarius A star grew radically brighter over the course of a single night, a flare attributed to a smaller clump of infalling material meeting a sudden, violent end near the horizon. These episodes offer a brief, real glimpse of what a fully active accretion disk would deliver constantly, rather than occasionally, around a black hole that feeds in earnest. The first object ever seriously proposed as a black hole was discovered precisely because of this glow. Cygnus X1, identified as a powerful X-ray source in 1964 and confirmed through subsequent observation across the following decade, became the subject of a famous, friendly scientific wager between physicists Stephen Hawking and Kip Thorne, with Hawking betting half seriously against its being a true black hole. Hawking eventually conceded the bet in 1990, as accumulating evidence made the case for Cygnus X1's true nature essentially undeniable. Its accretion disk remains, to this day, one of the brightest, steady X-ray sources visible from Earth, an object roughly 6,000 light-years away, announcing its presence not through visible light at all, but through the violent glow of matter being shredded and heated on its way toward an edge it will never cross back from. Gaia BH1, fortunately for the purposes of this particular thought experiment, is something considerably rarer and quieter still. Astronomers describe it as a dormant black hole, meaning it currently has no significant accretion disk, no actively infalling matter, and therefore no intense radiation pouring outward from its immediate vicinity at present. This is precisely why it was so difficult to find in the first place, and precisely why its discovery method, watching the wobble of its visible companion star rather than searching for X-ray emission, represented something genuinely new in the search for black holes. Most of the black holes known before 2022 were found because they were feeding and glowing as a result. Gaia BH1 was found because of gravity alone in the relative silence of an object with nothing currently falling into it. In simple terms, the very quietness that made Gaia BH1 hard to detect is also what makes it survivable in this thought experiment to approach at all. A ship traveling toward an active, feeding black hole, one surrounded by a luminous accretion disk, would face lethal radiation doses from X-rays and ionizing particles, long before tidal forces or event horizons became relevant. A death by radiation exposure delivered from a comfortable, ordinary, otherwise survivable distance. This becomes even more extreme around the largest black holes that actively feed. M87 star, the supermassive black hole imaged for the first time in 2019, produces a relativistic jet, a tightly focused beam of particles and radiation launched outward from near the black hole's poles at speeds approaching the speed of light itself, observed and documented extending more than 5,000 light-years out from the galaxy's center, an almost incomprehensible distance for a single coherent structure to maintain. Anything caught directly in the path of such a jet would face radiation levels far beyond anything survivable, regardless of distance from the horizon itself. So suppose, having survived the distance, the relativistic dust, and the silence of Gaia BH1's dormant state, sparing the ship from the radiation that would have ended the journey around almost any other known black hole. The ship continues falling. The tides have already done their work, somewhere outside the horizon, on any version of this journey involving an object of stellar mass. But suppose, for the sake of the one question physics actually cannot yet answer, that the ship crosses the boundary anyway, intact, having somehow survived everything that came before it. What happens then is not a matter of insufficient data or unfinished measurement. It is a matter of a question current physics has never been able to fully resolve. So arrive, finally, at the question. This entire journey has quietly been circling from the very beginning. What actually happens after the crossing? Here, honesty requires something uncomfortable. Most of this script has been able to lean on settled, well-tested physics, the kind that has survived a century of observation without contradiction. This part cannot. Beyond the event horizon, physics does not go silent because we lack the instruments to look. It goes silent because our best theories, general relativity and quantum mechanics, the two pillars of modern physics, begin to disagree with each other in ways no one has yet fully resolved. The trouble began, in its modern form, in the work of the physicist Stephen Hawking, beginning around 1974 and 1975. Hawking discovered, through a careful combination of general relativity and quantum field theory, that black holes are not perfectly, permanently black after all. They emit a faint, slow trickle of radiation, now called Hawking radiation, caused by quantum effects occurring right at the boundary of the event horizon itself. Over almost unimaginably long timescales, far longer than the current age of the universe, for any black hole of significant mass, this radiation would cause a black hole to lose mass and, eventually, evaporate entirely. This discovery, elegant as it was, opened a much deeper and still unresolved problem. According to quantum mechanics, information, the complete physical description of everything that ever fell into a black hole, should never be truly destroyed. It might become scrambled beyond any practical hope of reconstruction, but in principle, it should still exist somewhere, recoverable, if only theoretically. But if a black hole eventually evaporates completely, radiating away as nothing but a thin, featureless trickle of Hawking radiation, what happened to all of that information? Did it leak back out, encoded somehow in the radiation? Did it simply cease to exist, in direct violation of one of quantum mechanics' most fundamental principles? This is known in the physics literature as the black hole information paradox, and it remains, to this day, genuinely unresolved. The problem sharpened considerably in 2012, when four physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper proposing what became known as the firewall hypothesis. Their argument, built on careful, rigorous mathematics, suggested that preserving quantum information might require the event horizon to behave not as the gentle, unremarkable boundary general relativity predicts, but as a wall of extraordinarily high-energy radiation, a firewall that would destroy anything crossing it instantly, contradicting the long-standing assumption that a falling observer would notice nothing unusual at the moment of crossing. This is not settled, it is not resolved. Different groups of serious, credentialed physicists currently favor different resolutions, including ideas involving complex mathematical relationships between distant points in spacetime and other proposals that remain by their own author's admission, incomplete. No experiment has been performed, or currently could be performed, that distinguishes between these competing ideas. This is one of the genuine open frontiers of physics, not a settled fact being simplified for a casual audience. So let the not knowing simply sit here for a moment, exactly as it sits in the physics itself. We do not know, with confidence, what a falling observer would actually experience at the moment of horizon crossing. We do not know whether the gentle, unremarkable crossing predicted by general relativity, the version this script has used throughout, or the violent, instant destruction proposed by the firewall hypothesis, is closer to what would actually occur. Both possibilities currently coexist in the technical literature, neither fully ruled out. The disagreement itself, a kind of honest signpost, marking the exact edge of what physics, in its current form, is able to tell us. And yet, even granting this uncertainty, even setting it carefully aside the way the rest of this thought experiment has required, general relativity's own equations continue to run, mathematically, past the horizon, toward a single point that the theory itself describes as the true and final destination of anything that falls. So follow the mathematics where it leads, knowing now, honestly, that the journey there carries an asterisk physics has not yet been able to remove. General relativity's equations, run forward past the horizon, converge toward a single point at the center, a location where, according to the theory itself, density becomes infinite, and the curvature of space-time becomes infinite as well. Physicists call this point the singularity. It is worth sitting with what an infinite value inside a physical theory actually means, because it is easy to misread, and the honest reading is more interesting than the dramatic one. When a respected, well-tested theory predicts an infinite, undefined quantity at some specific point, the standard, sober interpretation in physics is not that nature contains a literal infinity. It is that the theory itself has reached the edge of where it remains valid, and is signaling, through its own internal mathematics, that some other, deeper description must take over before that point is actually reached. General relativity does not claim to be the final word on physics. It claims, very precisely, where its own authority runs out. This is not a unique or unprecedented situation in physics. Earlier theories have hit similar walls before and been replaced or extended by deeper ones. Classical physics, before the early 20th century, predicted nonsensical, infinite results for the energy radiated by hot objects, a problem known at the time as the ultraviolet catastrophe. That breakdown was eventually resolved not by accepting an actual infinity in nature, but by the development of quantum mechanics, an entirely new framework that explained the same phenomenon without contradiction. Many physicists suspect the singularity at a black hole's center represents a similar signal, an indication that general relativity, brilliant and well-tested as it is, needs to be combined with quantum mechanics to correctly describe what is actually happening at such extreme densities, rather than an indication that the universe truly contains a point of literal, physical infinity. The combined theory that would do this, often called quantum gravity, does not yet exist in a complete, experimentally confirmed form. Several serious candidate frameworks are under active development. String theory proposes that fundamental particles are not points, but tiny, vibrating strands of energy, and that this different foundational picture might resolve the infinities that plague general relativity at very small scales. Loop quantum gravity proposes instead that space itself is not smooth and continuous, but made of discrete, finite units at the smallest possible scale, which would mean a true infinite density is mathematically impossible to ever actually reach. Neither framework has been experimentally confirmed, neither has been ruled out. Both remain active, contested areas of theoretical research, decades into serious development, without the kind of definitive evidence that would settle the matter. What we do know, with mathematical certainty rather than speculation, comes from the work of physicist Roger Penrose, whose singularity theorems, developed beginning in 1965, proved something important and often misunderstood. Penrose did not prove that an infinitely dense point definitely exists inside every black hole. He proved that, given fairly general and reasonable assumptions about how matter behaves, general relativity's own equations guarantee the formation of some kind of singularity, some breakdown of the theory's predictive power, once an object collapses past a certain point. This work earned Penrose a share of the 2020 Nobel Prize in Physics. It tells us that something has to give, mathematically. It does not, on its own, tell us precisely what replaces the infinity once a more complete theory arrives to explain it. So here is the honest, complete answer to what waits at the very center of the journey. We do not know. Not because the question is unimportant, and not because no one has tried seriously to answer it, but because the answer requires a unification of physics that has not yet been achieved by anyone, despite the focused effort of multiple generations of some of the most capable scientists who have ever lived. And the same unknown that sits at the center of Gaia BH1 sits, identically, at the center of every other black hole ever formed. The same equations, the same breakdown, the same honest admission of a theory reaching its limit, repeated at the heart of every collapsed star, in every galaxy, across every epoch of cosmic time, scattered through a universe that has been quietly producing this same unanswered question for more than 13 billion years. And so the journey, in the end, was never really a journey toward a place. It was a journey toward a boundary, and every fact gathered along the way, the distance, the radiation, the tides, the slow disagreement of clocks, the open argument still unresolved among physicists about what waits at the threshold, all of it converges on the same quiet realization. The destination was never the point. 1,600 years would pass on the worlds left behind. However the journey there was actually accomplished, however much of that time the travelers themselves experienced, as compressed or stretched, or simply lived through, hour by ordinary hour. Entire civilizations could rise and pass into history in that span. Entire languages could be born, spoken, and forgotten. And at the end of all of it, after the distance and the radiation and the tides had each taken their turn testing the limits of what a fragile, carbon-based traveler could survive, what would remain is not a destination reached, but a boundary acknowledged. A line in the geometry of space, drawn by gravity itself, past which the universe simply declines to answer any further questions. This is, in its own way, the most honest thing science can say about a black hole. Not that it is empty, not that it is nothing, but that it is the one place in the entire observable universe where our most successful theory of reality openly, mathematically admits that it does not know what happens next, and where the only intellectually honest response is to say so plainly, rather than filling the silence with comforting invention. There is something almost peaceful in that admission, if you let it settle the right way. The universe is not obligated to be fully knowable. It has corners it keeps to itself, boundaries it does not explain, places where the light that has traveled for thousands of years to reach our telescopes simply stops, mid-sentence, having delivered everything it can and nothing more. Most of the universe's history, billions of years of it, unfolded long before anything capable of asking these questions existed at all. And most of it will continue unfolding long after anyone capable of asking has gone quiet too. A black hole is simply where that ordinary cosmic indifference becomes total, complete, and permanent, all at once, in a single sealed boundary. And perhaps that is the real difference between fear and the kind of awe this subject actually deserves. Fear assumes the unknown is hiding something monstrous behind it, something that would harm you if only the curtain were pulled back. But the honest unknown at the heart of a black hole is not hiding a monster. It is simply a place where the map runs out, the way every map, even the best ones, eventually reaches an edge with nothing drawn beyond it. Cartographers of an earlier age used to write the same simple words across those blank spaces. Here be the unmapped. Not here be dragons, not necessarily, but simply, beyond this point, we do not yet know, and have not yet found a way to know. 1,600 years of travel, gathered into a single sentence, would end here. Not in destruction exactly, and not in arrival exactly, but in the simple, settled fact of a question the universe was never going to answer, no matter how far, or how carefully, or how patiently anyone traveled toward it. You are lying somewhere safe right now. Wherever that is, whatever room, whatever hour, your body is still, your breathing is slowing, and none of the distance we have just traveled together has moved you an inch from where you actually are. And yet, in a way that matters more than it might seem, you have just made the journey. You followed it the whole way, past the limits of any engine humanity has built, past tides that would end a body before a horizon ever could, past a disagreement between clocks that would outlast every person who ever loved you, to a boundary that our best theory of the universe admits. Honestly, it can't see past. You went as far as anyone has ever gone toward that question, without leaving the room you are in. What would actually happen in the end is this. The distance alone would outlast any human lifetime. The radiation around almost any black hole but the one quiet exception we chose would end the journey early and without ceremony. The tides, near an object as compact as Gaia BH1, would finish the work radiation left undone, sometime before the boundary was ever reached. And if, somehow, none of that happened, if the ship and its impossible shielding and its impossible engine carried someone all the way to the threshold itself, the universe would not greet them with destruction or revelation or any answer at all. It would simply stop talking, stop explaining, stop offering anything further for our equations, our instruments, or our oldest and most patient curiosity to hold on to. Picture, one last time, a single point of light, very far away, very old, sitting at the center of a darkness so complete that even light, the fastest and most reliable messenger in the universe, can't find its way back out once it crosses. Picture the silence around it, not as something hostile, but simply as the universe declining, gently and permanently, to finish a sentence it started 13 billion years ago. You will likely never travel there. No one you know ever will either. But the not knowing, it turns out, is not a failure of the search. It is simply where the boundary of all human knowing happens to sit tonight. Quiet, patient, and unmoved by anything we have asked of it so far. Sleep now. The universe will still be there in the morning, keeping its secret exactly as carefully as it always has.